Guess we can begin. So let me introduce Eric. Eric Martin has a PhD in physical organic chemistry from Yale University. He has worked in computational drug design and herbicide design for over 30 years. Eric is best known for starting the now widely practiced field of combinatorial library design. He is currently developing novel methodologies for the two areas of drug discovery, which are rational oral bioavailability design and protein family virtual screening, also known as PFVS. The former guides improvement of oral exposure during lead optimization by applying global sensitivity analysis to physiologically based pharmacokinetic simulations. PFVS computer models achieve accuracy comparable to experimental high-throughput screening by combining all historical activity data from entire protein families, work for which Eric was awarded the lifetime title of Novartis leading scientist. It's great to have you here, and I'm really looking forward to it as, primarily because both the things that you've been doing is something that we've looked into before. So looking forward to your talk, Eric.
Thank you. Can you hear me?
Yes, and we can see your slides as well.
Super. Okay, so appreciate this opportunity to tell you about using Profile-QSAR for safe collaboration between competing companies. I'm going to cover three topics. The first is applicability domains in machine learning. The second is multitask modeling. And the third is collaborative or federated modeling. So for applicability domains, this plot shows the correlation, R squared, between predictions and experiments for random forest regression models trained on chemical substructural fingerprints for 12,000 Novartis dose response assays. And it looks really good. The models were trained on a random 75% of the data and tested on the remaining random 25%. And the median correlation is 0.35, explains 35% of the data, and 60% of the models reach a level of explaining 30% of the variance in the data, which is sort of our rule of thumb for a successful virtual screen. But there's a problem, and this is how most people test their machine learning models on random held out test sets. But there's a problem for drug discovery, which is that these box plots summarize histograms of the similarity of each compound in that random test set to the nearest member of the training set. And you can see that most of the compounds are in this kind of 90% similarity range. The red box plots show the same result, but for the compounds that project teams actually ordered from 18 virtual screens that I did, and they ordered almost nothing from those highly similar predicted actives to the ones they already knew about. Instead, they were ordering compounds as different from what they knew about as possible. They were interested in chemical novelty. So that means that these random held out test sets really have nothing to say about how these models are going to perform in the way that the project teams are actually using them. So I needed to come up with a different way of dividing the training and test sets that would be more informative. This plot on the left shows a random held out 25% of the data, the red stars, and you can see they're all very close to the blue circles, the 75% training set, in the usual way. Instead, I clustered the data, trained the model on the 75% of compounds from the largest clusters, and tested it on the remaining singletons and very small clusters. And now you can see that the compounds are not touching the blue circles. And this now is the results for the same 728 models that were done in the random test sets. But now the similarity of the test set to the training set really nearly mirrors that of what actual projects did. And so this should give a realistic measure of how well these models should perform in practice. And now the results are very different. This blue line is the one you saw before. The red one is this realistic test set. And now the median correlation is basically nothing. And 93% of the assays fail to meet our successful produce models that meet our criterion for a successful virtual screen. And so the problem clearly is the applicability domain of the model. The data that are available for any given assay only cover a very small part of the chemical space covered by the entire company archive, and the scientists are only interested in that unsampled region. So we faced this problem actually back in 2005. Postdoc David Sutherland and I hypothesized that we could write the activity of any assay as a linear combination of the same compounds on all of the other assays. And we created Profile-QSAR, a massively multitask stacked model. So we start with what is now a matrix of 12,000 assays and almost 2 million compounds. And we want to use the activities, these are experimental activities, we want to use the activities of the compounds on these assays to build models for all of the assays. But we can't do that because this is 99.9% missing values. And so we add an intermediate step. We first build a conventional single task model, in this case random forest regression models built on substructural fingerprints, the very same models we were looking at before. That's going down the columns on whatever data is available for each assay. And then we use those models to fill in all of the missing values, to impute the missing values. And now we can describe each compound not by its chemical structure, but by its profile of mostly predicted biological activities, and train, in this case, a partial least squares regression model, a second model for each assay. So that's why it's a stacked model, because the output of the initial models are used as the input of the subsequent models. And because of this two-step procedure, every single one of the nearly 20 million experimental IC50s helps inform each prediction of each compound on each assay. And the improvement is pretty dramatic. The median correlation now is 0.53, and almost 3/4 of the assays meet our criterion for a successful model. And to put this 0.53 in perspective, I found 5 assays that had been done at a 4 concentration medium throughput IC50, and then in a much more careful 8 to 12 point IC50 measurement for lead optimization, and the average correlation was 0.54. And so these are comparable to a medium throughput 4 concentration IC50 on realistically novel compounds. So that's great. We've now expanded the applicability domain instead of from around the compounds that have been tested on each individual assay to basically cover the entire Novartis corporate chemical matter. On the other hand, it's limited to the Novartis chemical matter because the models still have an applicability domain. It's just been expanded to all of the compounds that we have studied. Wouldn't it be great if we could get all of the big pharmaceutical companies to combine all of their chemical structures, their targets, assays, biological activity data, and then we could build a Profile-QSAR that would cover all of the chemistry that's been studied by all of the pharmaceutical companies. That would be especially, that would really expand things, because anecdotal evidence from mergers of companies to form larger pharmaceutical companies have shown that corporate archives usually have only about 5%, maybe as much as 10% overlap between their chemical collections. Of course, that's never going to happen. The chemical structures, biological targets, and biological activity data are among a company's most carefully guarded trade secrets. But it turns out with Profile-QSAR, they don't have to share all that information. They can get the exact same result in a very safe way. So imagine we have 10 companies, each of which has, say, 1,000 assays. Each company, behind its own firewall, builds the single assay models These don't have to be random forest regression models based on chemical fingerprints. They can be any kind of model that that company feels safe with, and then share those as compiled black boxes. They don't have to describe what the targets are. They're just compiled programs that take a smiles in, and then they produce a vector of 1,000 numbers out that are activities on some target, but who knows what. They then each exports its 1,000 models outside their firewall into some public space. So now there are 10,000 black box models, and each collaborator now imports those 10,000 models, uses them to predict the activities on their own compounds, and then uses that now super profile of activities as the compound descriptors to build the final Profile-QSAR models, PLS models on each of their assays. And this is exactly the same algorithm that would be used, the exact same operations, as if they had actually shared all of their data, except that the calculations have been distributed among the several players, and each company only gets to end up seeing the models for their own assays, not for each other's assays, which is probably what they want. Now, this isn't we're not the only people who have thought about collaboration by sharing partial models. In fact, in Europe, the IMI has a consortium called MELODY, which is comprised of 10 large pharmaceutical companies, 8 nonprofits. It's a 3-year program. They have a $20 million budget. They're 1 year into that. Actually, Novartis, we are one of the participants in that large consortium. But still, at this point, nobody has actually been able to do this and to study the results. It would be hard to study the results because nobody has all of the data. So I wanted to understand, how does collaborative modeling really work? What can we expect in the outcome? And Novartis was created by the merger of 4 smaller companies: Ciba, Sandoz, GNF, and Chiron. And so this project was to test how collaborative modeling works by pretending that each of these companies collaborated in this way, because we have all of the data. Unfortunately, as Whitney was describing, annotations in databases aren't always the best, and we didn't have annotations about where all of the Novartis compounds came from, or the assays. So we had to do some archaeology to try and guess some of that. Some of the Ciba, Sandoz, and Chiron compounds we could identify because of the ID formats that had been used. For the GNF compounds, we could assign some of those to GNF based on if the chemist that registered the compound had been a GNF employee, and the rest we had to just assign to Novartis. With the assays, it was actually worse. All we could do was assign each assay to the company which had tested the most compounds on that assay. And as you can see, most of the compounds and most of the assays end up with Novartis labels. And there are 2 problems with this, with what we had to do. The first is that, of course, a compound could have been tested on many more Novartis compounds than the original smaller company after the acquisition, and so too many assays got assigned to Novartis. And the other is that we noticed that there was almost no compound overlap, less than 1% between each pair of companies. And as I said, we understand from anecdotal evidence, including within Novartis, that there should be more like 5% overlap. Nevertheless, this is what we could do, and so we went forward. For each pseudo company, we assigned the inside assays to its inside profile, and the other 4 companies' assays got assigned to the outside profile. And then for each assay, compounds that had not been assigned to that company, we called external compounds, and they formed an external test set. And compounds that had been assigned to that company were internal compounds, and they got split 75-25 using that realistic algorithm into a training and realistic test set. And then we built Profile-QSAR models using 3 different profiles. We used just the inside profile that would correspond to doing Profile-QSAR but not collaborating, using just the outside profile, and using the combined profiles, which is more or less, which is exactly actually what I showed on the earlier slide about how the method works. And finally, we compared that to the individual single assay random forest regression models. And the first thing to notice is that the brown bars on the right, the random forest regression models, are always the shortest bar. So that means multitask modeling always helps. And the next thing to notice is that for the internal test compounds, the blue bar, the inside profile, is always as good or better than any of the combined or outside profiles. And so that means that collaboration never helped predictions on internal compounds, which was kind of disappointing. But looking at the external compounds, predictions on external compounds, there we found that for the 4 smaller companies, there was a real advantage to using either the inside or combined profiles, using Profile-QSAR. For the much bigger Novartis, that didn't make any difference, that it was so dominated by its own large number of assays and compounds that the much smaller number of additional compounds and assays didn't help. So to address the problem of having one great big company and a bunch of smaller ones, we took a subset of 540 random Novartis assays, that was an average number of the other 4, and repeated the calculations. And now in this case, the benefit to Profile-QSAR on internal compounds, which is really substantial, actually is much less for Novartis. And I think that has to do with the diversity of taking such a small random subset of such a large, diverse set of assays. But still, we basically see the same situation, that the collaboration didn't help internal compounds except a little bit for Novartis. Again, though, for external predictions on external compounds, we did see an advantage for the smaller companies, including a small advantage now for Novartis. Now there was no advantage for GNF. GNF is now the largest company, now that Novartis has been shrunk. So again, it's a very, qualitatively basically the same result. So there are 3 problems with what we've done so far. The first, as I've already mentioned, is that there's almost no overlap between the collections of these smaller companies. The second is that this is now a collaboration between 5 small companies, and we want to know about collaboration between large companies with lots of compounds and assays. And the third problem is that the smaller companies are also the older companies. And so there's a qualitative difference between the compounds that had been synthesized before drug-like rules were really well established back in the 90s and early aughts. And also there were different kinds of assays. The newer Novartis company includes epigenetics assays, transcription factors, kinds of assays that weren't much studied when those smaller companies were working. And so to address all 3 of those problems, we combined the GNF, SIBA, Chiron, and Sandoz assays to form a super pseudo company, GCCS, which had 3,500 assays and 660,000 compounds. And then moved 1,000 of the 8,300 Novartis compounds over to GCCS. And then assigned either 15, 40, or 70% of those compounds to also be GCCS compounds, so that they would be overlap compounds to create different amounts of overlap. The amount from normalized by Novartis are shown here, 4, 12, and 21, and for GCCS, 5, 13, and 23% overlap, and then repeated the calculation. And even with artificially enhanced overlap, we find that the internal compounds predictions, again, there's a big improvement to using multitask modeling, but it does not benefit from collaboration. And also for both companies, the external compound predictions do benefit from collaboration, although not nearly as much. And even with these large amounts of overlap, it's not as much. And also the amount of improvement increases with the amount of overlap. From the GCCS point of view, removed compounds are the ones that have most of the overlap. And so we also looked at those independently, and they go up to even 40% overlap for the 1,000 moved assays when we moved added labels to 70% of the compounds. And even so, the improvement well, the improvement increases with overlap, but it's still never, the improvement over the, due to collaboration, doesn't get nearly as big as for internal. No, that's, yeah, the improvement by collaboration on these external compounds doesn't get as big as the improvement due to multitask modeling on internal compounds. So there are some conclusions. One is that Profile-QSAR is a natural fit for collaboration by sharing models. The benefit of collaboration was tested by using these 4 smaller constituent companies that merged to form Novartis back in the 90s and aughts. There's a huge benefit to using Profile-QSAR, or multitask modeling method, for internal compounds. And in that case, disappointingly, there's no additional benefit from collaboration. But on external compounds, there is a benefit. If there's a large company and smaller companies, only the smaller collaborators benefit. The benefit for external compounds increases with overlap, but it never gets as great as the benefit for internal compounds. There is a caveat. We only tested, because of the data we had available, we could only test collaboration between 2 large companies with substantial overlap. If there were more companies, the chance that your external compound would be in one of their collections would be increased. On the other hand, the number of descriptors for each compound, which are the predicted activities in the profile, also greatly increases. And so therefore, the curse of dimensionality becomes worse, and it's hard to anticipate which of those would really dominate. The other thing is, we've compared Profile-QSAR to a large number of other multitask modeling methods, like multitask deep neural networks, meta-learning models, and found that the results are extremely similar. And so we think that these results are going to be general to any methods of collaboration by sharing partial models, or even by sharing the actual data, because Profile-QSAR, the algorithm, is identical to what you get if you could actually get companies to share the data. There's a publication in review, but there's a preprint in Chem Archive if you want to look further. A couple of problems that need to be resolved. One is reverse engineering of those black box models. So random forest regression models and many of the modern nonlinear modeling methods give the highest prediction to compounds very similar to the most active compounds in the training set. And so using random forest regression would probably not be a good idea, because you could imagine using generative chemistry to generate compounds very similar to your competitor's most active compounds, which would be obviously a problem. But methods like ridge regression or lasso don't have that property. And so companies need to think about what methods are going to use. Each company chooses their own. I mentioned the problem of the commons, that smaller companies benefit at the expense of larger companies who don't. And one way to deal with that is, say I put out 100 models and you put out 1,000 models, is I only get back 100 of your 1,000 black box models, so that's fair. The problem with that is that it would incentivize me. A good thing is it would incentivize me to publish as many of my models as I can, but it would also maybe incentivize me to cheat, that I could use phony data to build my models, or use public data from Kemble or something like that. So it might be necessary to have a data auditor, so that each company has to prove that they actually have the data that backs up their models. And I want to point out that these problems are going to be common to any method for multitask modeling. It's not specific to this method, but those are things that have to be dealt with. So I need to acknowledge the many co-developers of Profile-QSAR, a parade of postdocs. David Sullivan, who I mentioned, built the first version in 2005. He's now at Numerate. Jeet Mukherjee was a subsequent postdoc who's now at Gilead, and Li Tian was a third postdoc who actually went on to work for Novartis in Singapore and then in Shanghai, but eventually she's now at Tencent. Jin Liu was not a postdoc. He was an intern that worked with Li. He's now a graduate student at Oxford. Valery Polyakov was not a postdoc. He's a very senior computational chemist who collaborated with me for many years. He's now at Sutro Biopharma. And finally, Shenwei Zhu, who is my current postdoc working with me, and he's the person who did all of these calculations. I didn't do any of these calculations, and so he deserves the real credit for these results. And finally, it didn't take a village to build these multitask models, these Profile-QSAR models. It took a metropolis. And so I really need to acknowledge the thousands of Novartis chemists, assay biologists, and IT specialists who synthesized all these compounds, developed all of these assays, measured all of these activities, and built the computer systems that could store all of this data and do these non-trivial calculations. And so with that, I welcome your questions, comments, criticisms, or anything else that comes across your mind.
Awesome. Wonderful. Thank you so much for presenting, Eric. Again, like you said, I'm glad you showed the acknowledgement slide. I am familiar with Valery with Sutro Biopharma. We actually invited him to the conference today. I'm not sure if he's in the audience right now, but he's definitely one from the West Coast that we sent an invite to. And if there's anyone that has a question for Eric, Dr. Dabanu, or anyone.
I just had a quick comment, Eric. That was great. I think I really liked how you did this modeling and testing with 5 companies that came out of Novartis or precursors of Novartis. An excellent idea. It was nice to see that innovative way of getting data and testing it out.
Thanks.
Wonderful, wonderful. All right. So with that said, thank you again, Eric. Dr. Dabano and everyone, I guess we'll be shifting gears to our next presentation with Victoria. Her room is from MG to KG, how leveraging integrated discovery and development capabilities can smooth your past IND and beyond. So if we can all head over there, I would appreciate